Good afternoon. So we are starting officially the module number 4, though there are certain small things are pending in module number 3. So we will keep on doing that because all these modules are too much of entangled, intervened. So while doing module 4, again we will go back to module 3 and we'll keep on doing it. So here I am showing actually the module 4 content. So you will be finding that there are mainly three contents in module 4, and this is the biggest chapter. It takes quite a lot of time to finish that chapter, and it's fully numerical. So a lot of different numericals we have to do. Today we will start with the first case. So there are mainly three parts in this module number 4. So first part is absolute asymptotic. So absolute stability analysis by classical method. We have already seen that. We have seen that if all the poles are in the left hand side of S plane, in that case the system is stable. So as the pole are shifting towards right, the system is getting unstable, and as the poles are shifting towards the left side of S plane, the system is getting more stable. Now only this much does not suffice. There are a lot of other logics and things to know about stability. So this first part, so actually they're explaining what is meant by absolute stability, asymptotic stability, relative system stability, Routh, Hurwitz stability, and everything. So Hurwitz stability criterion, this is what we are going to see today. So what is absolute, what is asymptotic, what is relative stability, all those things we'll keep on seeing slowly. But mainly there are three topics. If you see, first one is the Hurwitz stability criterion, or it is called as Routh Hurwitz stability criterion. I think you have seen this thing partially in network analysis. There is a circuit theory and all, which was there in third semester. And then there will be fourth topic. Then there will be second topic, which is called as root locus plot. So this generally eats up quite a lot of time. Previously, we used to say that 8 to 9 lecture they used to give on root locus, but we will do it with the help of MATLAB. So tomorrow immediately we cannot start it because there are a lot of steps. So there are mainly 2 or 3 different types of root locus. So 10 steps we have to carry out in root locus, almost in every numerical. So every numerical at least 6 to 7 steps we have to carry out. Their standard steps. So at least 4 or 5 numerical we will see on root locus, then only we can go for lab. And lab is very easy actually. In one command, that is rlocus, you can find out what is the root locus from the given GSHS. So I told you that GSHS, open loop transfer function, is a very important thing. So I'll give you GSHS. You can find 1 plus GSHS, which is called as characteristic equation, and then you just apply the formula of rlocus or syntax of rlocus. That will give you root locus plot. But you will find that to draw root locus plot initially, you will take at least 40 to 45 minutes. Okay, but later on, whenever you are doing in the exam, it should not take more than 20 minutes to draw root locus plot. So that expertise we have to develop. So that is the second topic, root locus, and third topic is called as Bode plot. So Bode plot is actually the frequency domain analysis of stability for any system. So root locus is the Laplace domain analysis of stability of any system. Bode plot is the frequency domain analysis. So here we have to use the semilograph paper. So these are the mainly three topics. First is Hurwitz stability criterion, second one is root locus, and third one is Bode plot. So on this 4 questions we set. So every paper will be having 4 questions in every module. So you have to answer any 2. So one question of 10 marks definitely you will find from today's topic, that is the Routh Hurwitz stability criterion, or RH criterion as we call it, Routh Hurwitz stability criterion. And there are different types of stability: absolute stability, asymptotic stability, relative stability. All these things we will be seeing when we are studying all these 3 different things. So what are the 3 main topics? Number 1 is Hurwitz stability, number 2 is root locus, and number 3 is Bode plot. Hurwitz stability and root locus, they are in Laplace domain. All the S and all these things will be there. So characteristic equation will be there, and from the characteristic equation in Hurwitz stability criterion, we have to find out whether the system is stable or unstable. So if there are poles in the right hand side of S plane for characteristic equation, we can say that system is unstable. We have shown why is it so. That is, whenever there is a right hand side pole, that will be producing some kind of a diverging kind of time domain response. And whenever we find there is a diverging kind of time domain response, we will see that this will actually generate energy under the curve as infinite. And if energy under the curve is infinite, that means that response actually is unstable response. And so that we will see in case of Routh Hurwitz criterion, root locus also we will see how to find out the stability, gain margin and all those things in S-plane. And third thing we will see Bode plot, that in in frequency domain, how can we find what is gain margin, phase margin and stability. So I am removing this syllabus, and there are two case studies also. So in third module also there is a case study. One we have done and one we are supposed to do. So third module, small things are pending. So some things I will record, upload. Some things we will do in extra time. This Saturday we will be having definitely an extra lecture session from 3 to 5. So please be prepared. So I'm removing this syllabus, and I will start with so I'll stop presenting this. I will start with the book of M. Gopal, and we will see what is meant by Routh Hurwitz criterion. So a 10-mark question definitely will be asked from this Routh Hurwitz criterion. So there are three cases. One is a very simple numerical, and second one, there are two special cases. So all those two special cases also we have to see in case of Routh Hurwitz. We will see how to find the stability by using Routh Hurwitz criterion. So just give me 1 minute, and I will launch the book. We are going to do it from the book of M. Gopal, and page number and everything I will show, I will tell you. And from there, we will be doing RH criterion and the whole stability part. So it is in the 5th chapter. So those who are having pen and paper, you can write down. It is in the 5th chapter of the book of M. Gopal that we will be doing this RH criterion. So I'm launching now the book. So you are all having this book already with you. So this is the control system book of M. Gopal. So I think my presentation is visible to you all now. So I guess it is visible. Yes, it is visible. So there, if you are coming to the first page, you will be finding that there is module number 5. Okay. So in the module number 5, whenever you are coming, you have to click exactly on the content. And if you are clicking on the content, you are directly going to module number 5. So this is the thing. Module number 5, just click on it and you will come to the module number 5. So this is a very good book, and it is very properly arranged and everything. So from this book, we are going to see what is meant by Routh Hurwitz criterion and stability. See, already you have seen this module. I think the book is visible. Any of you please confirm? I think the book is visible. Yeah. So last day we had done from module number 4. So today we are going to do module number 5. And this is actually the Routh Hurwitz criterion we are going to do. But before that, let us see some of the theories. And one more request to you. It is almost 10 minutes now, and students are still joining, and it's disturbing me. Next day onwards, after 5 minutes, you please don't request. I'm not going to admit you. Okay, so only 30 students are joining, and you are taking your advantage. So please do not join after 5 minutes. I will not allow, because allowing students, it really bothers me. It's disturbing. So after 15-20 minutes also students are joining. This is not right. So please, Abhishek Patil, what happened? Why are you 10 minutes late? Abhishek Patil, why are you 10 minutes late? So please don't request next time onwards. If you find it is 5 minutes, don't request. I'm not going to allow you. So please don't take too much of advantage of the situation. You are supposed to join at 2:45. 5 minutes is there. So you should join by 2:50. Don't be too much late. It doesn't feel good allowing students for first 20 minutes of the lecture. We are going to do this topic from the book of M. Gopal, and this is concept of stability and Routh stability criterion. Very important topic from exam. 10 to 15 marks definitely you can expect from this. So here they are giving the example and detail of stability. You can go through. We have actually seen this module because we had done this bounded input, bounded output stability. In the second chapter, we have done this. In the first chapter also, we have done this. What is meant by bounded input, bounded output? What is the area under the curve, finite energy? All those things we have seen. And then there is Ys by Rs. So from there, here, he has taken the Rs in the right side. He has found what is Yt. So many of the things like this we are doing for our lab as well as for our regular lecture. So YES is nothing but the step response. So whatever is the transfer function, that is multiplied with the input, and then YES, YT we have found. And this graph, I think you remember while explaining this pole to pole position to time domain response, I had shown you this graph. So if there is only one single pole on the left hand side of S plane, it will be a decreasing exponential. If there is only one pole in the right hand side of S plane, it will be a increasing kind of exponential for real poles. If there is a real pole at origin, that will be giving you us a UT, that is the unit step response. If there is a pair of poles, so only one pole they have shown here, so there is -2 plus 3j kind of thing. -2 minus 3j is also there. So in that case, we are going to get a diminishing kind of sinusoidal. This is called as underdamped sinusoidal. This is right side also. This is the underdamped sinusoidal, but this is increasing. Okay, in this case, it will be e raised to t sine t or e raised to at sine bt. So this will be a unstable waveform. Left side, this will be a stable waveform. And top, this is if you are finding there is a pair of pole on j omega axis, that means plus minus 3j. In that case, this will be generating a 3 radian per second sinusoidal waveform. So all those things we have seen. Left side of the S plane, it is called as stable. On the S plane j omega axis, it is called as marginally stable. Right side of the S plane, it is called as unstable. So all these concepts we have seen. Now directly we are going to go to the topic number 5.3 is also done, zero input stability and all those things. We will go for 5.4. So write on the page number is 222 from the book of M. Gopal. We will prepare this. So this is page number 222, you can find here. I will give my notes also, but if you want to know the theory, in that case you have to read it from the book. So not too much theory I will be wasting my time on. I will directly go for the numerical, what exactly you are supposed to do. So what is given? What is given is a determinant. So whenever you are doing all this delta and all those things, you'll be finding that if it is in a matrix form, so you still don't know what is matrix form. Matrix form we can find out whenever we are doing in the fifth chapter, whenever we are doing state space analysis. At that time, you'll be finding that characteristic equation is found from the determination of determinant of A matrix. But at present, you don't need to worry about what is meant by determinant. You just think that we have found CS by RS or YS by RS, that is YS by XS, output upon input. And there you are finding a denominator equation. And then the denominator equation is in the form of like this, that is A naught S raised to n plus A1 S raised to n minus 1 up to AN is equal to 0. So whatever is the denominator equation of a transfer function, that is called as, that equal to 0 is called as characteristic equation. So that characteristic equation should be given to you. So in the exam, what kind of numerical they are going to give, I will show you by my handwritten notes. But before that, let us just see it from the book. So what will be given to you? Given to you will be a transfer function. So it's a very simple numerical. Let us solve criterion and let us find out how to find out system stability from the Routh-Hurwitz criterion. So here we are finding a system transfer function. Okay, system transfer function means YS by RS is equal to something by something. The denominator of transfer function is equal to 0. So this S raised to 4 plus 8SU plus 18S square plus 16S plus 5. This is the denominator equation of a transfer function. And that equal to 0. That is the transfer function to characteristic equation. Now this characteristic equation should be given to you. In that case, just looking at it and just by doing Routh-Hurwitz criterion, you should be able to tell me what is the stability criterion of the system. So in this, you have to find out there are two parts. One is the even part, another is the odd part. What is the even part? S raised to 4 plus 18S square plus 5. This is the even part. Because here it is S raised to 0, 5 S raised to 0, 18S square and S raised to 4. So there are two parts in this characteristic equation. And one is the odd part. So you first have to separate the coefficients of the even part and odd part. So what is the highest? So how to prepare this table? This table is called as Routh-Hurwitz table. And from this table, from the first column, we can find out whether the system is stable or unstable. So how to do that? So S raised to 4. If it is S raised to 4, first start with S raised to 4. Okay, and then S raised to 4, this is the coefficient of S raised to 4, that is 1. And then there will be a coefficient of S square. Okay, because first we are writing about the polynomial which is called as an even polynomial. Why are we writing even polynomial first? Because highest order is 4. So this is a fourth order system, because I told you this is a transfer function, numerator by denominator, and whatever is the highest degree of denominator, that is called as system order. So this is a fourth order system. There are four energy storing element in this system. So that's why first I should write s to 4. And all these things you can write here also. So this is s to 4, s cube, s square, s to 1, s to 0. And it will go up to s to 0. All the numericals will go up to s to 0. If it was s to 5, then we could write s to 5, s to 4, s to 3, s square, s to 1, and s to 0. So whatever is the highest order, that you should start with, that value of s you should write here. So in this case, highest order is 4. That's why the even polynomial will come first. If it was s to 5, then odd polynomial would have been our first line. So in this case, s to 4 I have written, and after that what I am writing is what is the after that I am writing what is the coefficients. So first is 1 s to 4 plus 18 s square. This is 18, okay, because the odd polynomial will go in the next line. So this is 8s cube. So this 8 goes in the next line, and this 18 comes in the first line, and this 5 comes in the first line. So what are the first line? And students make mistake here because they are not observant. So first line is the all the coefficients of the even polynomial. Even polynomial is s to 6, s to 4, s to 2, and s to 0. So this constant means 5 into s to 0. That is also a part of even polynomial. What is the odd polynomial? S to 1, s to 3, and all. So you have to divide this whole equation, characteristic equation, into two parts: even polynomial and odd polynomial. As highest polynomial is even, you have to start with highest even polynomial coefficient. So this is 1, 18, and 5. 1, 18, and 5. So this is the first line, and second line will be the odd polynomial equation. So second line will be 8 and 16. 8 and 16, and below this 5 you can write 0. Okay, so how to write this first two line? This is very important. So as it is 4 is the highest, you start with the coefficient of 1, coefficient of 4, that is 1, then there will be 18, and then there will be 5. It's very easy. And second line, after s4 there comes s cube. So here it is 8, and here it is 16. So this much part is done. Now you have to do some cross multiplication. So cross multiplication is exactly the same way we are doing the matrix multiplication or something, or I don't know how you do it. So okay, this is actually the opposite of matrix multiplication, because matrix finding determinant, what we do is 1 into 16 minus 8 into 18. Here it is reverse. Here you have to start from bottom left. That is 8 into 18. This you have to do first. So it is shown here minus top into bottom. So top left into bottom right. So you have to start from bottom left, go to top right, this 8 into 18, and second top left into bottom right. So minus and divided by this thing. So divided by this 8. So this is very important. So what is the denominator? Denominator is divided by this 8. So what will be the factor here? So s4 and s cube is given, because whatever is the characteristic polynomial given, from there we can find out what is the even part and what is the odd part. And after that we have to construct s square, s1, and s to 0. If it was s to 5 something, in that case s to 5 and s to 4 we could have got from the characteristic equation. In that case we have to construct s cube, s square, s to 1, and s to 0. And in exam they ask up to s to 7. So we will do some numerical, we will solve some numerical where we are taking up to s to 7. So if s to 7 is there, then first line will be s to 7, next line will be s to 6, then we have to construct from s to 5 up to s to 0. So 6 rows in that case we have to construct. So here only 3 rows we have to construct, and after that we have to check from the first column if there is any sign change. From there we can tell you whether system is stable or unstable. So first line is 1, 18, and 5. Second line is 8 and 16, and below 5 there is nothing, so you can make it 0. And then you go by bottom left to the top right minus top left to the bottom right. So 8 into 18 minus 1 into 16 divided by 8. Next is this 8 into 5. So always this first column will come into use. So 8 into 5 minus 1 into 0. So you can see here, this is a very good example, page number 225. This is the first example directly. You can start from example only, because in exam they will be asked numerical on Routh-Hurwitz criterion. And even if they are asking theory, that also there are two special cases. So today we will see the normal cases of Routh Hurwitz and what are the uses of Routh Hurwitz. Special cases we will do tomorrow. That is day after tomorrow. So in the second line, it is 8 into 5 minus 1 into 0 divided by 8. So 8 into 5 minus 1 into 0 divided by 8. So what is the third row first column? It is 16. That is 8 into 18 minus 1 into 16 by 8. If you calculate, it will come down to 16. And student makes very silly calculation mistake that is unpardonable. So whenever this kind of Routh-Hurwitz numerical is there, it's the easiest kind of numerical. Please don't make symbol mistake. Please don't make calculation mistake. Because if you are making mistake in calculation and values, automatically it will cause symbol mistake. And if there is a symbol mistake, then stable system becomes unstable, unstable system becomes stable. So please don't do any mistake in calculation. Check the calculation twice, because 10 marks, easiest 10 marks you can score in Routh-Hurwitz criterion. So this is first thing is 16 and second thing is 5. So this is 8 into 5, that is 40 minus 0 divided by 8. So this is 5. So now the third row first column is 16, third row second column is 5. Now what we have to do is this third row and second row. So what now we have to do is here, whatever we are writing, next row. So this is 16 minus 16, sorry, 16 multiplied by 16 minus 8 multiplied by 5. So you can see here. So this 27 by 2 comes later. Okay, so as they have done in the book, they have written first 27 by 2, but वो बाद में आता है. पहले क्या आता है? 16 multiplied by 16 minus 8 multiplied by 5 divided by 16. So if you are doing that, in that case, you are going to get 27 by 2. And what is the next line? Next line is 16, 5. Now this is 16, 5. So this will be nothing. So here it will be 0, because in this case, it will be 16 multiplied by 0. So this is 16 multiplied by 0 minus 8 multiplied by 0. So everything is 0. So if you are finding that third row is 16 and 5, that means in the next row, it will be only the first element, because next row first element is 16 multiplied by 16 minus 8 multiplied by 5 by 16. This is 27 by 2. What is the next line? This is 16 multiplied by 0 minus 8 multiplied by 0 divided by 16. So that will give you 0. So here it is 27 by 2. It doesn't stop here. It goes to the SS to 0. So every numerical you have to come to SS to 0. How to find it? So this is 27 by 2 multiplied by 5 minus 16 divided by 27 by 2. So it will be 5 only. Okay, so this is how the table is constructed. Please check it. If you don't do numerical, you will not understand. So nobody can show this numerical and make you understand. Only thing is, you can understand this table from your understanding, and it is as simple as this. So don't get confused. What are the different specific cases, special cases? There you might get confused. So I will tell you how to tackle those special cases. So there are two special cases. If time permits, we will do today. Now this table is constructed. Now this table is constructed. How to find out whether this system, which system? The system whose transfer function is given by this. What is the transfer function? S to 4, 8s cube, 18s square, 16s plus 5. From there you have first divided into even polynomial, odd polynomial. So first line is 1, 18 and 5. Second line is 8 and 16. And below 5 you can give 0. From there you can find out these other factors. So this is 16, 5, 27 by 2 and 5. So these are four things you have to calculate: 16, 5, 27 by 2 into 5. And you have to go reverse of the way you find the matrix determinant. So matrix determinant, you find this top left multiplied by bottom right minus top right multiplied by bottom left. So here exactly reverse you have to do. You have to start from bottom left to the top right. This is the first multiplication, minus top left to the bottom right. That is the second part. And you are finding this table. Now after finding this table, you have to comment whether the system is stable or unstable. How to check that? You have to check this first column. Okay, this is a very important thing. You have to check the first column, and if there is no sign change in the first column. Now very important thing I'm telling you, a lot of people will say everything should be there in the first column positive. No, if all the components in the first column are negative, then also it satisfies Routh-Hurwitz criterion. And if Routh-Hurwitz criterion first column is satisfied, means system is stable. And what is meant by first column satisfied? It means that there should not be any sign change in the first column. There should not be any sign change. That means if top and first and second thing are positive, third, fourth, fifth, all things are positive. In this case, what we have to say is, after forming this table, we have to say that in the first column of Routh-Hurwitz table, we are finding that all 5 elements are positive. More than positive, what we have to say is all 5 elements are having same sign. That is more accurate. Okay, so in the after finding this table, what we have to say is it's a table, Routh-Hurwitz table we have constructed, and the first column is having 5 elements, and all 5 elements are having same sign. वो पॉजिटिव है कि नेगेटिव है तुमको बोलने की कोई जरूरत नहीं है. Just say that all 5 elements in the first column, they are all of same sign. And the rule is,
Sir, how
if we are
S0
finding that,
calculated?
pardon,
Sir, S0 how we calculate it?
S0. So this is 27 by 2 multiplied by 5. Okay, 27 by 2 multiplied by 5 minus 16 into 0 divided by 27 by 2. Same rule, 27 by 2 multiplied by 5 minus 16 multiplied by 0. So 16 multiplied by 0 means it is 0. So it is 27 by 2 multiplied by 5 divided by 27 by 2. That means 5 is remaining. Understood?
Yes, sir. Yes, sir.
ठीक है, so एक बार खुद लिखो, then it will be easier for you to understand. So this is 27 by 2 multiplied by 5 minus 16 multiplied by 0. That means 16 multiplied by 0 means it is 0. That means the first thing stands, 27 by 2 multiplied by 5 minus 16 into 0 divided by 27 by 2. Same rule, whatever we have done here. Okay, here. So this will be 5. Then we have to say that the first column of the Routh-Hurwitz criterion, there is no sign change. There is no sign change means what? Number of sign change. Now this is a very important thing. There is no sign change means what? No sign change means there is no pole in the right side of S-plane. If there were two sign changes means suppose this was 16, this was minus 27 by 2, and this was 5. So 16 to minus 27 by 2, I'm talking about other numerical. Suppose this 27 by 2 is negative. After finding from the third row, you are finding that in fourth row, some negative thing is coming here. Suppose this was minus 27 by 2. In that case, there are two sign change. Okay, and last thing was 5. So 16 to minus 27 by 2, there would have been one sign change, and minus 27 by 2, there would have been another sign change. So there are 5 elements in the first column. If another numerical, I'm saying this 27 by 2 was suppose negative, then there are two sign changes. 16 by 27.217, one sign change, and 27 by 2 to 5, there was another sign change. So two sign change means there are two poles in the right hand side of S-plane. That means system is unstable. But in this case, you are finding that there is no sign change. No sign change means no pole in the right hand side of S-plane. That means all the poles are in the left hand side of S-plane. So the system will be stable. Now see another thing, another characteristic equation. So more number of numerical you solve, you will understand. So this is the first numerical. First prepare the Routh-Hurwitz table. Check the first column. If there is no sign change in the first column, that means there are no poles in the right hand side of S-plane. So what is the number of sign change in the first column indicate? So you can write down number of sign change in the first column indicates number of poles which lie in the right hand side of j omega axis. Again I am repeating, number of sign change in the first column indicate number of poles which are there in the right hand side of S-plane. In this case, first column all are positive, all are same sign. That means there is no sign change. Some RH criterion can be all signs are negative. So this is minus 1, minus 8, minus 16, minus 27, and minus 5. That means all the components in the first column all are negative. Then also there is no sign change. Means all the poles are in the left hand side of S-plane. So positive है कि negative है ये देखो मत first column में. Just check if there is positive to negative or negative to positive. If there is any sign change. Number of sign change in the first column is directly proportional to or is equal to the number of poles which are lying in the right hand side of S-plane. And whenever there is a pole lying in the right hand side of S-plane, means system is unstable. So this is what is Routh-Hurwitz criterion. Consider the second characteristic equation. So here is also, this is 3s to 4, 10s cube, 5s square, 5s2. So what will be the first line? First line will be S4, second line will be S cube, the same thing. In the first column there will be the same thing. So what will be in the first line? 3, 5 and 2. And what will come in the second line? 10 and 5. So you can check here. So follow this numerical only. Okay, so check what is there in the first line. First line is 3, 5 and 2, and second line is 10 and 5. So whenever you are writing 10 and 5, you can reduce it. So 10 and 5, you can divide the row by 5 and you can write 2 and 1. So instead of 10 and 5, you can write 2 and 1 because they are multiplicand of each other. So So 10 is the multiplication of 5, so you can make it 2 and 1. So this kind of things will make your calculation easy. So in this case, this kind of things are allowed. So what is now our first row? First row is 352. Why 352? Because if you see the polynomial, so this is the characteristic equation which is given. So I can give you GS HS. I can only give you GS, what is HS, and I will not give you characteristic equation directly. So you have to first calculate what is the GS divided by 1 plus GSHS. From there you have to find out what is the denominator equation. Denominator equation is equal to 0. That will be the characteristic equation. And from the characteristic equation you have to first separate out the even and odd terminal. So even is 3, 5 and 2, 3, 5 and 2, odd is 10 and 5, 10 and 5 you are reducing it to 2 and 1. Now do this Routh polynomial and you just find out what is it. So first is 2 into 5, that is 10 minus 3 divided by 2. Okay, so this is 5 into 2, this is 5 into 2, minus 3 into 1, so minus 3 divided by 2. So what you are finding is, first thing is 7 by 2. Next thing is 2 into 2, that is 4, minus 3 into 0, that is 0, divided by 2. So second will be 2. Okay, so this 2 into 2, minus 3 into 0, that is 4 minus 0 divided by 2, that will be 2. So what is the third row now? Third row is 7 by 2 and 2. What is the second row? Second row is 2 and 1. So now find the s raised to 1 coefficient from s cube and s square. What will it be? 7 by 2 multiplied by 1 minus 2 into 2. So that is what they have do. They have done 7 by 2 multiplied by 1 minus 2 into 2. Who is this? मजाक चालू है तुम लोगों क्लास का. Okay, so this is 7 by 2 multiplied by 1. So this is 7 by 2 multiplied by 1 minus 2 into 2. Okay, so that is what is done, divided by 7 by 2. So if you're doing it, it comes to be minus 1 by 7. And the last line is minus 1 by 7 into 2 minus 7 by 2 into 0 divided by minus 1 by 7. So last line is this 2. Whatever is this 2, this comes here. So you just do this table once and you will understand how to find it. But main important thing is just check what you have to do as the conclusion. So as conclusion, you have to say that there is s raised to 4. S raised to 4 means there are 4 poles in the system and 2 poles are lying in the right hand side of S plane. This you have to tell. Why 2 pole? Because check that this is positive, this is positive, this is positive. 7 by 2 is positive. And from there 7 by 2 to minus 1 by 7. This is one sign change. So after doing the Routh table, you have to say that 7 by 2 to minus 1 by 7, this is one sign change. And next line, minus 1 by 7 to 2, this is another sign change. So from s square to s raised to 1, this is one sign change from positive to negative. And lastly, from s raised to 1 to s square, there is another sign change from negative to positive. So there are 4 poles. How there are 4 poles? Because characteristic equation is having power, maximum power is s raised to 4. So there are 4 poles. Out of that, 2 poles are lying in the right hand side of S plane. Why 2 poles are lying in the right hand side of S plane? Because there are 2 sign changes in the first column in the RH criterion. So this is what you have to understand. It is written here. It may be noted that in order to simplify the computational work, S cube row is divided by 5. This modifies the row 2 to 1. Examining the first column of the Routh array, it is found that there are 2 sign changes. What are the 2 sign changes? From 7 by 2 to minus 1 by 7, this is one sign change, and another from minus 1 by 7 to 2. So it is found that there are 2 sign changes. Therefore, the system under consideration, which system? Whose characteristic equation is given to us. So therefore, the system under consideration is unstable with 2 poles in the right hand side of S plane. I will say it in the other fashion. I will say that there are 2 sign changes, so this line is correct, and then I will say that there are 2 poles now in the right hand side of S plane, and as there are 2 poles in the right hand side of S plane, the system is unstable because a single pole in the right hand side of S plane for the closed loop system will make the system unstable. In this case, there are 2 poles which are in the right hand side of S plane. Now this actually settles the score, and this says that the system is unstable. Itna hi bolo. So there I asked actually 2 questions. First question, whether find out system is stable or unstable. So if the system is stable, then there is no problem. All the poles will be in the left hand side of S plane. There are no poles which are there in the right hand side of S plane. Matter settled. But if you are finding there is sign change, in that case, number of sign change is equal to number of poles which are lying in the right hand side of j omega axis. So I ask two questions. First question is, so I give you a polynomial. First question I ask is whether the system is stable or unstable. So first you have to say it is unstable. Then question is how many poles are there in the right hand side of S plane. So if you are finding there are three sign changes, you have to say that system is unstable because there are right hand side pole, and there are three sign changes, that means there are three poles which are lying in the right hand side of S plane. So this is what is Routh Hurwitz criterion. So this is very simple numericals what we have done. Let us see a complex numerical. Check here, it has gone up to s raised to 6. Okay, so special cases also you can find towards below. So our special case we कर डालते हैं. Next we will solve some numerical, or I'll give you some numerical for practice, and that itself will complete this Routh Hurwitz criterion. So there is nothing very difficult in this case, only repeated case and all those things. So let's see how it is. So s is to 6, 4s is to 5, 3s is to 4, 2s cube, s is to s square plus 4s plus 4. A very important thing I'm telling you, there may be this 4s missing. In some cases, there may be this 4s missing. So in that case, you have to assume that this is s raised to 0 into 0. Okay, so this s into 0. So in that case, you have to assume that part as 0. So I will show you numerical where some event is dropped. So it is s is to 0, s is to 1, s is to 2, s is to 3, and accordingly it is going. In some numericals, suppose 2s cube is not given. So you cannot say that, sir, I'll assume it to be positive. No, this is not positive. So s cube is there with a coefficient of 0. So you have to assume that. So if s cube is not there, you have to assume s cube with coefficient as 0. So in that case, one element, so wherever s cube element is there, this one, and this element will be 0 in that case. Anyways, so in this case, just write down what is the Routh Hurwitz table. So first is 1, that is s is to 6. Next is 3, that is s is to 4. Next is s square, this is 1, and this is s is to 0. Okay, so this 1, 3, 1, 4. So this is 1, 3, 1, 4. This is the first row. What is the second row? So first row is now even polynomial, and second row is the odd polynomial. Odd polynomial is s is to 5, s cube, and s. So what are the coefficients? 4, 2, and 1. So you can find here it is 4, 2, and 4, 0. Sorry, 4, 2, and 4. I'm sorry. So this is 4, 2, and 4. So this is 4, 2, and 4, and you can divide by 2. So you can make it 2, 1, 2. 4 to 4 भी रखो तो भी result आएगा, कोई problem नहीं है. 4 to 2, 1, 2 करो तो भी same result आएगा. There is no problem. So now all the tables and everything is given to you. So let's find what is the s is to 4. So this is 2 into 3, that is 6 minus 1 divided by 2. So this is 5 by 2. So 2 into 3, that is 6 minus 1 into 1, that is 5 divided by 2. So this is 5 by 2. Next row is 2 into 1 minus 2 into 1. So next row is 0 because this is 2 and this is 1 and this is 1 and this is 2. So 2 into 1 minus 1 into 2 divided by 2. So that is actually going to be 0. Next is 2 into 4, that is 8 minus 0 divided by 2. So that is going to be 4. Okay, so be careful. These are the initial things you cannot understand. लिख लिख के करो तो अच्छा रहेगा. ये सब numerical देख के नहीं होता है. You have to practice Routh Hurwitz criterion on pen and paper. Then only you will be able to understand. ये जो numerical दिया हुआ है, यही numerical करो, but खुद के हाथ से करो एक बार. Then only you will understand. And please practice this because this is easiest 10 marks you can score in control systems. Okay, so this is 2 into 3 minus 1 into 1 divided by 2. So 2 into 3 is 6 minus 1 divided by 2. This is 5 by 2. Next is 2 into 1 minus 1 into 2. So numerator 0 ho gaya. That's why this is 0. Last one is 2 into 4. That is 8 minus 1 into 0. That is 8 divided by 2. That's why this becomes 4. So now whenever s is to 4 you have written, then s is to 6 is of no use. So as soon as you are writing s is to 4, s is to 5 is there. Then you have to prepare s is to 3 from s is to 4 and s is to 5. So what is that? 5 into 2 multiplied by 1. Minus 2 into 0 divided by 5 by 2. So this will be 1. So this is 5 by 2 multiplied by 1 minus 2 into 0. So minus 2 into 0 means 5 by 2 only. So 5 by 2 divided by 5 by 2. This is 1. Next is 5 by 2 into 2. That means this is 5. 5 minus 8. Okay. So 5 minus 8. That means minus 3. So this is 5 by 2 into 2. This is 5. I'm sorry. Minus 2 into 4. So 5 minus 8. That is it should be 5 minus 8. So this should be minus 3 by 2. So some negative thing should come here. So here it is actually happening. So 5 by 2 multiplied by 2. This is 5 minus 2 into 4. That is 5 minus 4 is 8 divided by 5 by 2. Okay, divide by 5 by 2. So that's why this 6 by 5 is coming here. And you can again do the table. So this is 3 into minus 6 by 5. That means minus 18 by 5 minus 4. So this will give divided by 3. So this will give you minus 38 by 15. So it is difficult. So if you are not solving, देख के वो समझता नहीं है. Once you do the hand calculation, it is easy. So now we are finding what? We are finding that it's a system with 6 roots. And 6 roots means it's a sixth order system. Sixth order system means there are 6 energy storing element in this system. Okay, so there will be 6 roots of this closed loop system. We have to find if there is any root which are lying in the right hand side of S plane for this closed loop system. So after finding this, what comment you have to give? So there are 1, 2, 3, 4, 5, 6, 7 element in the first column. Okay, so first you have to construct this table. For that, एक ही rule है, that is bottom left to top right minus top left to bottom right divided by bottom left element. ये एक ही rule है. There is nothing difficult, and by that same rule you have to find all this columns in the left hand side. So this is the first column. So first column, how many sign changes are there? So here 3 to minus 38 by 15. What is the value वो देखने की जरूरत नहीं है, सिर्फ ये नेगेटिव है इतना काफी है. So 3 to so plus to minus and minus to plus. That means there are 2 sign changes. So we are finding that this is a closed loop system with 6 poles, and out of 6 poles there are 2 poles. Why 2 poles? Because there are 2 sign changes. Why 2 sign changes? Because 2 to minus and again minus to plus. So this is 3 to minus 38 by 5. So positive to negative, 1 sign change, and again negative to positive, another sign change. So there are 2. That out of the 6 poles, there are 2 poles which are lying in the right hand side of S plane. That means the system is unstable. So it is written there, it is seen that the polynomial has the right half plane roots. How many roots? Since the element of the first column are not all positive, हमेशा positive होने की जरूरत नहीं है. All should be of same sign. Okay. So in fact there are 2 roots in the right hand side of S plane since there are 2 sign changes. So अगर ये ऊपर से सब negative होता, and this one would have been positive and last one is negative, in that case also there would have been 2 sign changes. So first column element should be positive. कुछ books में ऐसा लिखा रहता है. That is a wrong statement. All the first column elements should be having same sign. If all the first column elements are having same sign, that means there is no sign change in the first column. If there is no sign change in the first column means all the roots of the system are lying in the left hand side of S plane. That means system is completely stable. The number of sign change in this case, number of sign changes is 2. That means there are 2 poles which are there in the right hand side of S plane. That means system is unstable. Now let us find out what are the special cases. So first special case you are going to find out is a row of all zeros. So what are the special cases? So we write theory questions and we ask you to write with an example. So whenever you are writing, so this is another question. So there are mainly 2 questions which are asked in RH Criterion exam. First is I give you a polynomial. I ask you to satisfy or to carry out Routh Hurwitz criterion and to tell us whether the system is stable or unstable. So such 2 numericals or 3 numericals we have just checked. In that there may be a difficult case. That case there may be a, excuse me, in that case there may be special cases. So what are the special cases? I'm going to explain now. So first case is all row element is equal to 0. Understand it by some kind of numerical. Let me launch my numerical.
Yes, sir.
Okay, so it is written there are 2 special cases. So if you solve it by numerical, it will be easier for you. You can find out the theory from the book of M. Gopal, page number 244 or 222, whatever it was. So there are 2 special cases in RH criterion. First case is all element in a row is equal to 0. So for that, ये जो numerical है, ये numerical तुमको याद होना चाहिए पहले से. Because otherwise during exam you cannot invent this kind of numerical for which one whole row will go to 0. Okay, so you have to remember this. So this is a theory question. It has to be supported by numerical, but you have to remember this. So what is that? SS to 5, SS to 4, 2s cube, 6s plus 6. So you do that. So SS to 5 is 1, 2s cube is 2, and then this is 6. So 1 2 6, and what is in the second row? Second row is 1 and 6. So okay, 1 0 6. अभी यहाँ पे देखो, here I have dropped a square. Okay, so ये सब गूगली वाला न्यूमेरिकल है, ये सब याद रखना है. So this is s is to 5 s cube and s. So this is 1 2 and 6, 1 2 and 6, and here s square नहीं है. S square नहीं है means s is to 4, and then s square part is 0. S square part is 0 means I have to substitute with 0, and then there is 6. 6 is the s raised to 0 part. So I think this is understood. Then what you do is, first you do the s cube row. So this is 1 multiplied by 2 minus this, so this is 2, so this is 2, because this is 1 multiplied by 2, and I think I am doing a different case. Okay, so first element in a row is 0. So I'm actually, that was a different thing in a book. The first case was whatever was first case in the book, here it is second case. So I'm taking the first case as in this case, first element in a row is 0. Okay, in that case what happens? So first element 0 ho gaya, matlab what we do to the first element? Something divided by 0, that we do. So everything we are dividing by 0, that means every element will become infinity. So how to solve this? Let us solve this and we'll find out what is the problem. Okay, so this is 5 s is to 5 means 1, then s cube is 2, and then s is to 1. Okay, so this is s is to 1, this is 6, and then s is to 4 is 1, then s square is 0, and this is 6. Ye ho gaya. Then if you are solving for the s cube element, it will be 2 0 0, because this is 1 into 2 minus 1 into 0 divided by 1, so that will be 2. And then 1 into 6, that is 6, minus 1 into 6, again 6 minus 6 divided by 1, so this is 0. Third element is also 0. Now you are finding this 0. Okay, so how are you finding this 0? So this is 2 into 0 minus 1 into 0, that means 0 by 0 divided by 2, this is 0. So as soon as this thing comes, what to do? Okay, because what will be the next thing? 0 into 0 minus 2 into 6 divided by 0, so everything goes to infinity. So this is a special case. This is a special case that when first row element becomes 0, or first element of any row becomes 0. Okay, so you have to go up to that place. So you are finding, so you just do s5 s4 s cube, and you are finding s square is 0. What to do in that case? Replace this 0 by a very small factor. Replace this 0 by a very small factor, which is called as epsilon. So epsilon is very small, maybe 0.001 or something, which is almost equal to 0, and continue. Okay, so here s square ke samne you have to write what is epsilon. Okay, so in that case, in front of s square, what we have written is a epsilon, and then we are proceeding. So how to do that in that case? So this is s cube is 200, we have written. A square was 0 and 6. Instead of 0, we are saying that this is epsilon. So now again you prepare the table. So this is epsilon. Epsilon is not equal to 0. Epsilon is something little bit greater than 0, and generally we assume it to be positive. Somebody can say, sir, why aren't we assuming it negative? छोटा है तो negative भी हो सकता है, but generally it is assumed as positive only, because previous trend was positive. That's why we are assuming it to be a positive. Okay, so this is epsilon. So what is the next step? Epsilon into 0 minus 2 into 6, that means 0 minus 12 divided by epsilon. This is minus 12 by epsilon. This part is 0, and what is the last line? This is minus 12 by 6 into 6 minus epsilon into 0 divided by this, that means this is 6. What is the next line? A square is this. Why this is epsilon? Because this was 0, and instead of 0 we are assuming to be epsilon, and from here we are finding this into this. So this is 0 minus 12 divided by epsilon, which comes here. And what is the last line? Last line is minus 12 by 6 into 6 minus 0, that means 6 into minus 12 by 6 divided by minus 12 by epsilon. That will give my 6. So in this case, what is the first column? First column elements are 1 1 2, and then epsilon minus 12 by epsilon and 6. So what are the first column elements? It is 1 1 2 epsilon. So instead of 0 we are assuming epsilon minus 12 by epsilon and 6. So what is the conclusion now? So we will finish our lecture today by this one case only, but I will upload this numerical second case also. I will upload, you just check, so that Wednesday again we can discuss. So both the cases I will upload, so these 2 pages. So in this case, what is the first column element? 1 1 2 epsilon minus 12 by epsilon and 6. And what is the logic? First column elements are 1 1 2 epsilon minus 12 by epsilon and 6, as there are 2 sign changes. Where are the 2 sign changes? One is from positive epsilon to minus 12 by epsilon. This is one sign change. Another sign change is minus 12 by epsilon to 6. So as there are two sign changes in the first column, the system is unstable. And how many poles are there in the right hand side of the S plane? So you have to say that there are two sign changes in the first column of S plane. Hence, there are two poles which are in the right hand side of S plane. So system is unstable, and what is the degree of instability? There are two poles which are in the right hand side of S plane. And what is the last case? So I'll just tell you, I'll not show the remedy. So first you have to tell me the problem. What is the problem? Problem is if one first row element becomes 0. This is the problem. Okay, so what we are doing is we are doing the Routh-Hurwitz criterion. We are taking the bottom left, top right, and all those things we are doing. And then what is the problem? Problem is if the first row element becomes 0, then how to proceed? So you have to do first row element becomes 0. Instead of 0, we have to assume a very small positive number, epsilon, and we have to proceed. And then finally, we have to check the same thing. How many sign changes are there in the first column? Number of sign changes is equal to number of pole in the right hand side of this plane. What is the second case? Second case is you have to again take some kind of, so this numerical also you have to remember. So here it is 1, 8, 20 and 16. This is the first row. Second row is 2, 12 and 16. So 2, 12, 16. Likewise, if you are solving, one row whole becomes 0 element. So you are finding what is the problem. So problem is one whole row becomes 0 element. Then how to proceed? I'm not going to explain now because it's already time. So what is the problem? I have already told you. What is the second problem? Solution, how to proceed it, you can find from this solution. So this solution I'll upload today. From here, you just find out what is the solution. So on Wednesday, we will start from this numerical, that is one row has become completely equal to 0. Then how to solve for that and how to apply Routh criterion in that. So with that and with some more numericals, 3-4 more numericals on these two cases, we will finish off this first part of module number 4, that is the stability analysis by using Routh-Hurwitz criterion. I stop.